So in this video, we're going to do a hypothesis test example for independent samples. So of course we know that they're going to be independent, but we'll make sure we talk through why they would be independent samples in this specific example. So here we're looking at comparing two treatments for allergy relief. We want to see if the new treatment is significantly better than the standard treatment using a 1% significance level. So that's given us our alpha of 0.01. Out of 40 subjects, 20 were randomly assigned to each treatment. We recorded the time to relief. There's our quantitative variable. And it tells me to assume that things are normally distributed. So we're actually going to talk through a couple of things before we actually start going through and doing the hypothesis test. So first, let's sort of talk through why they are independent. So our two groups that we're comparing is we have this new treatment and we have a standard treatment. And it says out of our 40 subjects, 20 were randomly assigned to each treatment. So if I had John assigned to the new treatment, who now has to be assigned to the standard treatment? Well, it could be any of those other 39 remaining people, so he doesn't have a specific match. And we'll write that out more specifically when we get to the conditions. Another thing that we need to talk about to truly understand is what does it mean to actually be better? Now, what I mean by that, we're asked to see if the new treatment is significantly better than the standard treatment. Well, what is better, bigger or smaller? Well, I need to know what we're looking at. Well, we're measuring the time to relief for an allergy sufferer. So if you are an allergy sufferer, what would you like the time to be until you start feeling better, to feeling some relief? Well, in this case, better is actually going to mean that I want the smaller value. So in a sense, what we want to see is that the new treatment then will have a smaller time than our standard treatment. Or I could also say that the standard treatment would be larger than the new treatment. Those are both saying the same thing. Finally, the last thing to discuss here is the time to relief being normally distributed. So I've told you in the past, sometimes it could just be stated in the problem, versus sometimes you may actually have to assess histograms. So I actually stated it in this problem because I don't think most of you would look at these histograms and say that those look pretty normal. Now when we look at these two graphs, generally we can come to a consensus that they're relatively unimodal. This isn't really that big of a dip, so you kind of would just put a big old unimodal curve on it. The real question is, would you feel like they're symmetric? And that's usually where the question is. So another way we can see that the data is relatively symmetric is by comparing the mean and medians of our two groups. Remember, if the mean and median are close, that generally gives you a pretty strong indication that they're symmetric. And so the fact that our means and medians are also very, very close here would actually make me feel comfortable in describing both of these histograms as being unimodal and roughly symmetric. So these are ones where even if I did not say it was normally distributed in the problem, I would feel pretty comfortable in saying those graphs look unimodal and roughly symmetric. Now we can actually dive into doing the problem. So our very first step, of course, is to do our hypotheses. Now we discussed why they were independent, which we will of course be writing down in step 3. But let's talk through what our hypotheses will look like. Now really, in order just to match my StatCrunch output, I'm going to let the 1 subscript be my standard treatment and my 2 subscript be my new treatment. But we could have done it the other way. It wouldn't matter as long as we were paying attention to which one is which. So I also like to use the letter subscripts instead of the numbers just so I know which one is which a little bit better. So our null hypothesis for independent samples will be that the means equal each other. For the alternative, we've just got to figure out what sign we want to put between here. Now we really actually already have that sign when we discussed what better actually meant. And I listed the standard treatment first. So we want to hopefully show that the standard treatment then is larger than the new treatment, because then that would mean that the new treatment has a smaller time to relief, which would make it better. So then our sign here is going to be that greater than sign. And again, that sign is important to us because that's going to change our p-value when we go to StatCrunch. Our step 2 has not changed. So we are going to reject the null hypothesis and believe the alternative hypothesis if our p-value is less than our significance level, which was given to us to be 0.01. Next, we want to check our conditions. So we discussed why they were independent samples, but let's actually write it out. So there is no known reason, remember, because we assume independent until we know otherwise, to match the patients across the treatments. Now, how were these 40 subjects selected? It doesn't really tell us. Generally with medical studies, there's usually some federal laws and stuff that they have to follow. So for that reason, I'm going to assume that that's okay. Because again, they really didn't say much about how they chose them. So again, really no known bias going on here for us. Next, we either need to have both the populations be normal or have samples of at least 30. I first want to discuss that the second part of this condition is not met, because I need for my individual sample sizes to be at least 30. So individually, they're each 20. I don't get to combine these together and say 40. I have to look at them individually, and they need to each be at least 30, which is definitely not true here. So I do need my populations to be normal. Now again, why I'm going to say that that's okay is looking at those histograms. They're both unimodal and roughly symmetric. Again, not perfect, but pretty good. And then finally, both of the population standard deviations will be unknown. Notice we are given standard deviations, but these are the sample standard deviations, not the population ones. So now we can do our test statistic calculation. But just as we discussed when we were doing the confidence interval, we're going to primarily let StatCrunch do a lot of this math for us. But we'll plug everything in so you can see how it works. So we're going to take the y-bar of the standard treatment first, so 25.195, subtract off the sample mean of the new treatment, which was 20.925. Then we're subtracting off something and dividing by something. Again, what we subtract off is 0, because that null hypothesis is a 0 difference between them. And then we have our sample standard deviations and sample sizes to use in that bottom part. So we're going to subtract off 0. We're going to divide by the square root of 5.09 squared over 20 and 3.27 squared over 20. Now again, this top part, I expect that you could do that math okay. You would just get 4.27 for the top. Now for the bottom, you could do this by hand. This is where we want to use StatCrunch. So that bottom number is what we call that standard error. So this 1.353 number is what that bottom value is, that standard error. And this would give us a t of about 3.156, which you'll also see in our StatCrunch output. Next, for step 4, we'd want to calculate our p-value, where StatCrunch again is going to do our work here for us. But again, I like to draw the picture to really make sure we understand what's going on, because t and z are a lot alike. So our number of standard deviations away. This time our t is a pretty large number. It's 3.156, so it's way out here. My alternative, again, is a greater than sign. So I'm going to be shaded to the right of that value. And so again, when I actually go to StatCrunch, I'm going to have to give it my HA sign to give me the correct p-value. So our p-value coming from the StatCrunch output is 0.0017. Going back up to our step 2, that is then less than 0.01. Right, because start checking the numbers. So it is less. So we will reject the null hypothesis. We will believe the alternative hypothesis. So what does that mean for our interpretation? Well, our alpha is 0.01. Since we did reject, there is statistically significant evidence. To support. And then finally our alternative in words. Now what we were trying to show was that the new treatment was better than the standard treatment. Technically though, the average time. So there is evidence to support that the mean time to allergy relief is faster, better, whichever word you'd want to use, for the new treatment than for the standard treatment. So if you were to read this statement and you're an allergy sufferer, which medicine would you take? The new treatment or the standard treatment? Well, if you were to just read that statement, sure, new treatment's faster, let's take it. However, let's suppose, and this happens quite often, that a new treatment probably is going to cost more. So let's suppose that the standard treatment costs $20 a month, the new treatment costs $40 a month. What do you think now? So is it worth the extra $20? That's not really maybe a question I know the answer to yet. Yeah, it's faster. But something I might want to know is how much faster. And so that's why it might be great to look at a confidence interval as well. Is we know it's quicker, but how much quicker is it? Right, if it takes me 30 minutes to feel better with the new treatment and 2 hours with the standard treatment, that extra hour and a half might be worth me spending that extra $20 a month on. But if I don't know how much quicker, if it's 2 minutes quicker, maybe I'm just going to, save my extra $20. And so knowing how big of a difference it is important for us. So here in StatCrunch, I just created the confidence interval. I'm not going to go through all of the same steps since we've already done the steps for a hypothesis test here. What we're going to do is focus on reading the output and interpreting it. So things that are important to me for reading output is that it tells me which mean was which. This lets me know my order of subtraction here. So I know that we did the standard treatment minus the new treatment by looking at that. Also then what's going to be important to me is this L limit and this U limit. So again, first just thinking about the standard and the new treatment here. If I got a positive number, that means the standard was bigger than the new treatment, which meant the standard took longer to feel better than the new treatment. If we got a negative, the new actually took longer to feel better. And if we got 0, that would mean that they took the same amount of time. What I can see from over here that this is an all positive interval, which is telling me that the standard is greater than the new, which is telling me the same thing I already found here with the hypothesis test. So in a sense, that's not giving me any new information. So what's giving me the new information are the actual numbers that I see here. So I can now say that I am 98% confident that the mean time to allergy relief for the new treatment is between 0.959 and 7.581. What were my units? Minutes. Faster than for the standard treatment. So now, what do you think about paying the extra $20 a month for this new allergy treatment? Just on average, people are feeling better about 1 to 7.5 minutes sooner. And again, that's the average. So some people could actually be taking longer to feel better. Some could actually be maybe feeling better a lot quicker. But looking at this, if I was, for example, the drug company, and I saw that, okay, this new treatment that we spent this time and money working on average will make people feel better 1 to 7.5 minutes quicker, I don't know if people will actually pay to take this medication or not. So confidence intervals are sometimes a very important follow-up to do with a hypothesis test when we reject the null hypothesis. So we can see, well, how big is that difference between the two? In the last video, you're going to see us do some StatCrunch demonstration for how I got all the different output that you see here.